Good afternoon, my name is Julien Boulliung. I'm doing a postdoc at the University of Oxford under the direction of Bernard Wood, and today I will present you my results focused on sulfate solubility in silicate melts at atmospheric pressure with implications for sulfur degassing processes. We are interested about sulfur because this element is implied in many geological contexts, like for example in volcanic degassing with climate implications. This element is also implied in the formation of magmatic ore deposits and in planetary differentiation processes. For all these reasons, we need to better understand sulfur behavior in magmatic systems. We know today that sulfur in silicate melts have a speciation that strongly depends on the redox conditions, as you can see on the figure of the right, showing the ratio of S6 plus divided by the total sulfur as function of the redox conditions. We have two main speciation. For the most reducing conditions, sulfur is mainly incorporated as sulfide S2- according to the reaction at the left in blue, and for the most oxidant conditions above FMQ buffer, sulfur is mainly incorporated as sulfate according to the reaction in red at the left. In the literature, we mostly have data on sulfide solubility in silicate melts. However, there is almost no data on sulfate solubility as a function of the temperature and the melt composition. So the question I will answer today is how does sulfate solubility evolve as a function of the temperature and the silicate melt composition? To answer to this question, I did experiments in atmosphere control furnace from 1200 to 1500 degrees at 1 atmosphere in an air SO2 gas mixture with a log FO2 of minus 1.1 to ensure that we are under the sulfate regime. And I did the experiment with 14 different melt compositions. Then, as you can see at the top left of this slide, there is a picture of my final samples mounted in a resin, and I analyze the samples by two in situ methods. The first one, is the EPMA at the University of Oxford to determine the major oxide contents and the sulfur contents that are higher than 60 ppm. And for the lowest sulfur content, below 60 ppm, I did the analysis by SIMS in CRPG in Nancy in France. Before showing my results, I just wanted to show you that I reached the gas melt equilibrium during my experiments. So as you can see on this figure showing the sulfur content as function of the time, so I did a time series with two different melt composition, a CMS1, which is a iron-free composition, and a natural Icelandic basalt that is an iron-bearing composition. And as you can see, after 5 hours I reached the equilibrium. And for most of my experiments, I use a duration of 10 hours to ensure that I reach this equilibrium. Now, if we are looking at the results, here I show you a figure showing the log of the sulfur content as function of the ratio of the 1000 on the temperature. When this ratio increase, the temperature decrease. I put on the figure 1200 and 1500 degrees to better read this figure, this caption. And as you can see, when the temperature decrease, the sulfate solubility increase. For example, when the temperature decreases by 100 degrees, the sulfate solubility increases by a factor of 4. And as you can see here on this figure, I have 6 different melt compositions that show already different sulfate solubilities. That means that we have a melt composition effect on the sulfate solubility. We will look at that in more details a little bit later. And I will just use this slide to introduce another parameter I will use in the next slides. That is at the bottom left of this slide. It's the sulfate capacity, that is function of the sulfur content, the oxygen fugacity, and the sulfur fugacity. Now, if we combine the melt composition effect and the temperature effect on sulfate capacity, you can see here a figure showing the log of the sulfate capacity as function of the calcium content of the melt for 3 different temperatures from 1300 to 1400 degrees. And as you can see, when the calcium content of the melt increase, the sulfate solubility increase, and when the temperature again decrease, the sulfate solubility or sulfate capacity increase. So there is a dual effect of the temperature on the melt composition on the sulfate solubility and capacity. Now I use all the data from this study from 1200 to 1500 degrees to determine to develop an equation to determine the sulfate capacity as function of the melt composition. So you can see here the mole fraction of calcium, silicium, titanium, and aluminium, and as function of the temperature as well. And I obtain an equation with an R square of 0.98, that is quite good. And I show you here the figure showing the log of the sulfate capacity calculated as function of the log of the sulfate capacity measured. And you can see that the results are in good agreement. And now we can use this equation to simulate different scenarios for sulfur degassing from a magma into a water-rich fluid in oxidized magmatic systems. So here on this figure showing the sulfur amount remaining in the melt as function of the pressure. So to read this figure is actually a magma ascent. So we need to start at 250 megapascal. And I start the different scenarios with 2 melt composition, a basalt, andesite, with different initial amount of sulfur, 0.35 and 0.15, and at the same temperature, 1200 degrees, and I start with log FO2 of FMQ plus 2 that evolve with the degassing processes. And as you can see on this figure, at 100 megapascal, we have already degassed more than 80% of the sulfur from the melt. That is quite high. Finally, to conclude, sulfate solubility in silicate melt increases with the temperature decreases and with the increases of the calcium proportion in silicate melts. Now with this new equation, we can determine the sulfate capacity in silicate melts from 1200 to 1500 degrees at low pressure, and we can estimate the amount of sulfur degas during magma ascent in oxidizing magmatic context. Thank you for your attention.